If you took a glass of water and a needle, and you took that needle and you very carefully dropped it on the water, it would stay there. And it's not because it's floating. This needle would not be floating on the water. This needle is more dense than water, and we know that if it's more dense, then it should sink. So it's not floating. It's actually just sitting on the surface because there's surface tension. Water is a liquid that's capable of having a significant amount of surface tension. And you know it's surface tension because if you were to come in here and exert a little force down, breaking the surface tension or pushing this needle just below the surface, then it would sink. It would sink like a stone and just drop immediately to the bottom of the cup. So why does water have this property of surface tension? It has to do with the fact that the water molecules within this liquid are attracted to each other. This water molecule can form hydrogen bonds with the other water molecules around it, and it gets pulled toward them. And there's a term for this. We call this cohesion. So the fact that water molecules and other liquid molecules are attracted to each other is called cohesion. But what does this have to do with surface tension? Well, the key is these water molecules would like to bunch together. They want to group together if they can. So what would this water molecule do? I mean, which way is he going to go? How does he pick which one to group with? There's a problem. Here in the bulk of the liquid, he can't decide. Or in other words, let's just say got pulled toward this molecule. Well, it's also getting pulled to the left by all of this. By this one's pulling it back to its original position. This one's pulling it back to its original position because there will be a component of that force that'll point in the direction of its original position, as well as this one to the left. So these are restricted. These molecules here in the bulk of the liquid have too many other water molecules around them dictating where they need to be, because if they tried to get displaced, it'd pull them back to that position. However, at the surface, there's no water molecules above them. These are freer. They're less restricted. So that allows these water molecules on the surface to group together a little better, form stronger, tighter bonds, closer spacing at the surface in such a way that they form a tension that's not present in the bulk of the liquid. Yes, these water molecules down below will prevent them from just grouping into one big clump in the center, but since they're less restricted, they can form these tighter bonds here at the surface, and this allows it to support a pressure from above. So this allows it to support a certain amount of weight, which allows the needle to rest on the surface. A few practical applications of this, one clinical. If there's bile present in urine, you could detect its presence because it lowers the surface tension of urine. So it gives you a test of whether the liver is metabolizing things the way it should. Another application is if you go camping and you're in the tent, it's raining, and the tent gets raindrops on it. Most tents will keep the water from seeping through, but you're going to be tempted. You're going to be sitting in here, you're going to be like, that looks cool, and you're going to touch it, but you're not supposed to touch it because as soon as you touch it, you may break the surface tension. And once you break the surface tension, that water's dripping into your tent from that spot that you touched it, and you're probably not going to have a good night. So resist the urge to break the surface tension on your tent if it's raining out. And when you wash your hands, when we use detergents, if you washed your hands with just regular water and that's it, sometimes the surface tension's too great. These water molecules are too bound to each other. They form too big of a clump. It doesn't look like it. It looks perfectly smooth. But on a microscopic level, the water's not as diffuse as it could be. That's forming these clumps because the water has cohesion and it joins together. But if you add a little soap to the scenario, that breaks the surface tension. It lowers the surface tension, which means these water molecules don't clump together as much. And if they're not clumping together, they can get into the small cracks, which kicks out the dirt in your hands. And this water is better able to penetrate into the smaller cracks and get where it needs to go. So surface tension is due to cohesion between the water molecules at the surface of a liquid. But water molecules aren't just attracted to each other, they're actually attracted to the container too and other materials. And that's called adhesion. So the fact that water molecules are attracted to other materials as well is called adhesion. So what happens is this water molecule isn't just attracted to the other water molecules, it's attracted to the wall, and these water molecules climb the wall a little bit. So that's why you'll see when you fill a container with water or you're measuring an amount of liquid in a small burette, it's not perfectly level at the surface. It actually forms this kind of shape like that. This is exaggerated, but the sides will be a little higher than the middle. So you have to be careful when you're measuring. This is usually called the meniscus, and it's caused by the adhesion, the attraction of water molecules to the container that it's in. This adhesive force, this adhesion force is important. It causes something called capillary action. So let me get rid of this. And if you have a container with liquid, or say water, and you took another container, you put it in here like a straw. If you just stick it in, what you'll see is that because the liquid is attracted to the walls of this inner container, it doesn't just stay at this level, it'll rise above. It pulls this up a little bit above the surface level of the water. And if you took an even smaller diameter tube and put it in there, the smaller the tube, the greater this effect, and you'd get this water rising to an even higher level within this tube due to the adhesion to the walls of this container. And the name for this effect is capillary action, which is important in a variety of biological and non-biological examples where fluid is being aided in transport partially by the attraction to the walls of the container or the tube that it's flowing in.